So adjacency lists are one way of representing graphs, and the next way to represent graphs is an adjacency matrix. For a simple graph, we have a matrix where the entries are either 0 or 1, indicating that there is an edge or there is not an edge between these two vertices. So again, you need to have an enumeration to define this matrix. Here I'm using the natural order A, B, C, D, E. And since this is a simple graph, I do not have any loops. Therefore, you do not see any ones on the main diagonal. And also, you see that this matrix is a symmetric matrix. Obviously, because if there is an edge between A and B, then that also means there is an edge between B and A, because the edge is not directed. Therefore, this edge here is represented by this one as well as this one. Now, the adjacency matrix for multigraphs and digraphs can be formed in a similar fashion. For multigraphs, allowing loops, the only difference is that now the entries can take values apart from 0 and 1. So for instance, between B and C, here I have two edges. Therefore, between B and C and B, obviously, we have the entries of 2. Now, for a multigraph, this matrix is still symmetric because the direction is not important. But when it comes to digraphs, the matrix no longer needs to be symmetric because now the direction matters. For instance, I have an edge from A to B. Therefore, I have a 1 here, but I do not have an edge from B to A. Therefore, you see a 0 here. Okay. Well, obviously, if you have loops, you would have a 1 on the diagonal. And if you have multiple edges between two vertices, let's say, if I have this edge here between D and C, but let's say I have another one from D to C, this here would be, instead of a 1, this would be 2. So this is how you construct adjacency matrices for graphs in general, which brings us to the final way to represent a graph. And this is the incidence matrix. Here, again, this is a matrix, but it's not a square matrix because now in adjacency matrices, both the rows and the columns represent vertices, but in incidence matrices, the rows represent vertices, but the columns represent edges. You simply list the incident vertices to each edge in this matrix. For instance, E1 is a loop, so the only vertex incident to E1 is V1. Therefore, I have a 1 here, but all zeros in the rest of the column. With E2, the incident vertices are V1 and V2, so I have 1s here, and the rest is 0. E3 is between the same pair of nodes, therefore I have the same column here. E4 is between V2 and V3, so I have the 1s here, and so on. Similarly, E8 is a loop, so you just see a single one on that column. Okay, so to summarize, on the rows, you represent vertices, and on the columns, you represent edges. For instance, if you look at the rows, take this one, for instance. This means V3 is adjacent to edge number 4 and edge number 5. As expected, I have E4 and E5 adjacent to vertex V3. Now, for directed graphs, this definition differs from source to source, but take E2, for instance, edge 2, that is from V2 to V1. Therefore, the vertex that the edge emanates from is marked with -1. and the vertex it ends at, V1 here, is marked with a +1. Okay, so at each edge you see one +1 and another -1, except for the loops where you see no ones, in which case you understand that E1 and E8 are loops, but you cannot understand which nodes or which vertices they are adjacent to. So in case of a directed graph, uh, where loops are allowed, incidence matrix may not be the best solution to represent these types of graphs.